Okay, we reach our final section in topic 6, where we're going to learn about Poisson distribution. As in binomial distribution, that entails a very specific type of experiment that leads to some observations, which would be our variable. Also here, Poisson has a very specific experiment, so let's learn about that. So, what's a Poisson variable? Remember, in the binomial, it was number of successes in a certain n number of trials. Here, it's also number of successes. Usually, these are occurrences, all right? But we also call them the successes. But here, where are these occurrences? They happen in a certain interval of time or space. Okay, so that's the main difference between a binomial and Poisson, if you want. Some examples. The first example, we use it a lot in when we study a waiting line system in operations management, where usually arrivals, whether here it's arrival of cars to a certain petrol station or the arrival of customers to a certain bank or arrival to a restaurant. These usually follow a Poisson distribution. Another example that entails an interval of space, number of accidents that happen within a certain stretch of the highway. It can follow a Poisson distribution. So these are the characteristics of a Poisson experiment. First of all, the independency. It's very important that whatever occur in one interval has no influence at all, or it's completely independent from the number of occurrences or successes in the other interval. Then, second one, the probability of a success in an interval is the same for all equal size intervals. So if we're talking about time interval, the number of arrivals within 1 hour, let's say, for example, between 9 and 10, it will be the same as the number of arrivals between 10 and 11. Third, the probability of a success is proportional to the size. So if we say that on average the number of arrivals to the bank in an hour is 20 people, because of the proportionality, that means we can conclude that the number of arrivals within half an hour is exactly 10, right? Because 10 is half of the 20. The last one, as the interval gets smaller and smaller, the number of occurrences approach 0, which of course comes from the third, the first property, because we're talking about proportionality, right? So let's have some example to illustrate the use of a Poisson distribution. Okay, so but before we do the example, we did not learn yet how to calculate the probability. So we said that x is our variable. It represents the number of successes or occurrences in a certain period of time or space. So this variable is discrete. It has very specific or very limited number of values, and the probability of x, okay, where x is the number of successes, it's equal to exponential to the power minus mu. We'll talk about mu in a second, times mu to the power x, where x number of successes, over x factorial. So what is mu? Mu is the average number of successes in that interval, and usually we have that from past data. Okay, and the variance in a Poisson random variable is equal to the mean, which is very specific to the Poisson distribution. Okay, let's do some examples. Okay, so in this example, we're talking about number of errors that usually happen in a textbook that consists of 100 pages. So this is very important, and I'm going to highlight that later on. But for now, we are given that the number of errors are on average 1.5 for every 100 pages. Remember, we talked about an interval of time or space. So here, or a region. So this is a region, right? It's a 100 pages of a textbook, and we're given that the mean is 1.5. So this is mu, right? So mu is 1.5. We need that. So the instructor is randomly selecting 100 pages of the new textbook, and the question is what the probability that there are no typos. And when we define x as being number of errors in 100 pages, so we're talking about p of 0 here. Okay, I'm showing you here the equation that we use to find the probability of x, just to remind you how to do it. And now let's do p of 0. So p of 0, it's exponential minus 1.5, because 1.5 is our mu, right? And that's why I told you it's very important to know what is the mu that they are talking about. It's very important. Okay. And we multiply that by mu 1.5 to the power x, which is 0 in this case, over 0 factorial, and we'll get 22.3%. Okay, so let's continue with the example 7.13, which refer to the previous example 7.12. Okay, in the previous example, we were told that the mean number of errors in 100 pages is 1.5 errors. Now, the instructor has received a copy of a new book, and this textbook consists of 400 pages. Remember the proportionality aspect of Poisson experiment. Because now we're talking about 400 pages, so the interval is 4 times the previous interval. So you see, when we had 100 pages, mu was equal to 1.5. Now we're talking about 400 pages, and which means the average will be different now. So the average is now obviously 6, right? Because in 100 we have 1.5, in 400 it will be 6. This is our new mean, and now we can answer the question what the probability that there are no typos. Here mu is 6 errors. This is the equation again for you to as a reminder for you to use. Here we go. And p of 0, all what we do is to plug or to substitute x with 0 and the mu is 6 here, and we have a very low probability, because here we're talking about 400 pages, so that's a very 6 is very small number, right, in 400 pages. Second question, what's the probability that there are 5 or fewer? Okay, we did something similar before. 5 or fewer means that x is less or equal than 5. So we have to count or list the events that satisfy this condition. So it's a 0, 1, 2, 3, 4, and 5. So obviously what we need to do now is to find each one of these probabilities using that general formula, which is now I'm sure you're familiar how to use it. We have already found p of 0, so we need to find p of 1, p of 2, p of 3, p of 4, p of 5. Okay, and we sum these up and we find the probability of fewer than 5 or 5 or fewer is 0.446. Okay, so I hope that was clear for you. Okay, on a final note, as we also have seen in the binomial distribution, whenever we want to find a cumulative probability, it would be very efficient for us to look into tables. So also in your textbook by Keller, We have table number 2 in Appendix B that give us cumulative Poisson distribution. You may need to use that in the future. Thank you.